Assalamualaikum and good morning. My name is Muhammad Naim Muhammad Zahari. My project title is Explainable Defect Detection in Smart Manufacturing using Ensemble Learning. I am supervised by Dr. Muhammad Zaki bin Zakaria. So for background of study, machine learning models have become very common in smart manufacturing, where they are able to detect defects in products such as steel plates automatically. Although these models are very precise to locate faults, they tend to be black boxes. This implies that in cases where they are right, they cannot tell why a particular decision was made. The objective of this study is not to resolve this black box, but to have an effective explainability layer over it, an AI system that is precise and yet offers the actionable insights that engineers require to discover the root cause of defects. So for problem statement, we have three, which the first one, ensemble model such as XGBoost are highly accurate at detecting steel plate default, but they fail to explain why specific defect was identified or which features contributed to the decision. Secondly, the lack of transparency diminishes confidence among quality control department, hindering the AI adoption. Engineers cannot perform effective root cause analysis, creating a disconnect between AI outputs and the domain expertise. Teams are forced to merely react to identify faults rather than proactively optimizing the process to prevent them. Then lastly, the black box opacity is a well-documented barrier to the reliability and wider adoption of industrial AI. The goal is not to simplify the complex model but to build a powerful explainability layer on top of it. The layer will provide a human-readable, actionable insight necessary for genuine process improvement and defect prevention. Then for research questions, the first one is, what is the best way of optimizing an ensemble learning model to classify various categories of steel plate faults using tabular geometric and radiometric characteristics? Secondly, how does synthetic data generation method SMOTE affect the model performance references to identify minority defect classes in an imbalanced dataset? Lastly, what is the way sharply additive explanations can be applied to achieve global dataset level and local instance level interpretability of the defect detection model? For research objective, firstly, in order to design and train an XGBoost classifier that can detect several different kinds of steel plate faults with the UCI steel plate fault dataset. Secondly, in order to apply the synthetic minority oversampling technique to equalize the training data in order to obtain the model with high sensitivity of all defect categories, including defects that are uncommon. Lastly, to incorporate Sharp in the predictive framework to get visualization output that illustrate the model to make decisions to the non-technical stakeholders. For research scope, we have the data source from UCI machine learning repositories with 1,941 sample with 27 geometric and radiometric attributes. And our target is the 7 specific defect types of classification. For modeling approach, we will be using XGBoost model and explainability framework. We will be using Sharp using the three explainer method. Then lastly, for the development environment, we will be using Python, and the platform is Google Cloud, which is cloud environment with their key libraries like scikit-learn, XGBoost, Sharp, and Imbalance Learn. Research significance move beyond simple fault detection to root cause analysis. By pinpointing specific features, engineers can identify the exact machinery step causing the defect, enabling a shift from reactive repairs to proactive tuning. Secondly, to solve the black box skepticism by providing a transparent rationale for every rejected plate, allowing managers to adopt AI-based decision support system with confidence. Lastly, that to demonstrate a practical, factory deployable implementation of Sharp on tabular industrial data. So this is my literature review table. So this is my literature review mind map. So this is my research methodology where we have deliverables for each phases such as problem statement, literature review, UCI steel plate dataset, clean features and target classes dataset, XGBoost model architecture, system architecture, functional prototype, evaluation metric report, and finally, final year project report. So this is the system architecture where we have phase one, which is pre-processing, then phase two, where is the prediction model, then at the phase three is the explainability layer, then finally we have the phase four, which is the result generation. For expected outcome, the prototype is created and developed with Python and Streamlit. The interface is made user-friendly to the process engineer to enter 27 features into the interface. When they click on the button of predict, the data is scaled to make it valid, and then a library of sharp creates a real-time waterfall plot. Each plot demonstrates the defect type, graphically describes what particular characteristic inform that choice, and make the system transparent and trustworthy. This is my project timeline for the semester 1. This is my project timeline for the semester 2. This is the list of references that I have used in this presentation. Thank you.